basic inverter is also called a buffer. Who can tell me why it's also called a buffer? Does anybody have any idea?
Moderate the voltage that you're putting into it.
Okay, exactly. So let's look at this. What happens if we put two of them together, right?
You just change the voltage without changing the
It
sign.
comes out exactly. It comes out exactly the same. So if we put in something, let's say we had a really long wire or there was some distortion. So it's not quite a logic 1, all right? So it's not quite at 1 volt, it's at 0.8 volts. What's gonna happen here? Well, this bottom transistor is still like mostly gonna be on. So it's still mostly connected to this output. Okay, so there's this restoring force. So we get a 0 out of the first one again. And of course, we're then gonna get a 1 out at the end. So you see how it's a buffer? We're rebuilding the signal. All right, so here we have it. We've done it, digital logic. All right, we rebuild the signal integrity. We have consistent outputs. It's either a 0 or a 1. There's no this, no like 0.8 crap or anything. And it nicely chains together, as in we have these nice little blocks, and basically we have outputs of one, and we can chain them into the inputs of the next one. So do you guys see the binary? It's all zeros and ones. All zeros and ones. And you can ignore the small errors, which means that we can step back and ignore the analog world that it's built in, and all of a sudden we're in this fake digital world where everything's a lot nicer. So the CS people can really thank us for this one.
0.8 isn't quite high enough. 0.5.
Okay, yeah, so that's not actually a big problem because there's wide margins on these. So 0.5 is pushing it. But 0.5 would probably end up being, like, it would read as a logic 1 input. But if you're in between like 0.2 and 0.5 volts, it's in this gray range, and you don't want that because it can drain power, and you can get weird stuff at the output. So you're right that it's something you have to be careful of, but ideally your inputs will have buffers like this the whole way, so you're constantly, rebuilding your signal. Exactly. So that's a blank slide. Oh no, it didn't save any of my latest updates. That's a bummer. Okay.
Fly by wire.
Yeah, we're gonna do this. We're gonna do this.
Fuck it, we'll do it live.
Oh crap. Alright, hold on. Give me 1 second. Luckily I stole most of my slides from other classes. So we're gonna be fine. Alright.
Do you want me to zoom in on the slides or just stay out? Right now I'm not sure you can see the slides.
That's fine.
We've just got your pretty face.
That's cool. Okay. So here we have a more complicated gate, right? First we had the basic inverter, that was the most simple. Here we have a NAND gate. Alright, so we have 2 PMOS, 2 NMOS, and this is the schematic symbol, which is nice and tidy. It gets really complicated really fast, as you can probably imagine. But basically you need, if both of these inputs, A and B, are high, or logic 1, then the output is going to be 0. Otherwise, it's going to be a 1, right? So NAND means not AND. Okay.
Oh my god.
Okay. So we could step through all of this and I can show it, but it's not really that important. The idea is that we're building more generic logic functions out of these basic gates. Here's a NOR gate, so not OR. You can see here if A, B, or C are high, are at 1, logic 1, you're going to turn on any of these bottom transistors, and that's going to connect the output to 0. Okay? So if any of these are 1, your output is 0, is one way to think of it. So that's a NOR gate, right? Let's see. Okay. Alright, good. Starting from the beginning. So this right here, that is a full adder. And what that means is that there's 3 inputs. So you have A, B, and C, which are your 3 inputs, okay? So C is your carry bit from the last adder, that's not really important. But A and B are your inputs, right? You're trying to add them together, right? 1 plus 1, okay? So if they're both 1s, you want the output to be 2, right?
Mm-hmm.
And, well, I'm not going to be able to explain this to you, but it gets really complicated, obviously. But this is a full adder, so the yellow parts are PMOS. All right. The red is the polysilicon gate. Green is NMOS, and here we have our logic 1 and logic 0 sources. And here are the outputs. So the carry out and the sum. This is where, even here, it gets useless to look at the actual, it gets useless to live in the real world anymore. This is when you need to start going to computers. You know, we can lay all this stuff out, but it gets so complicated that you just need computers to do it for you. But that's a really cool example of, it's pretty cool looking too, but that's a complex example of how you can use these gates. Alright, so CMOS impacts, why is this a big deal? Well, basically it sets the digital standard. You know, this is what literally all of our electronics use, but it didn't have to be this way. Moore's Law, who's heard of Moore's Law here? Alright, that's pretty good. I've heard about it in just about every single one of my classes here. So Moore's Law is basically this theory that the size of the transistors is halving every few years. Or it's a little bit more complicated than that, but that's essentially the idea. And we'll look at that in a couple of slides. I found this might be a little generous, but 10% of the global GDP is based on this technology. And of course, this is what defines all of our processing power, which we use all of the time. And this is one of the latest innovations by Intel, and they've gotten down to 45 nanometers. I'm pretty sure they're way smaller now even than that, but a nanometer is 10 to the negative 9. So it's really small. So here's the number of transistors in a CPU by year. Notice this is a log scale, okay, so it's not just linear, it's exponential. Which is really remarkable, and it's allowed this industry to grow so consistently. And here's processing power. This is from Hennessy, of course. He's currently the president of Stanford. So basically, everything's getting faster. Hooray! Thanks to engineers. All right. This is my favorite example of Moore's Law. This is the PS2 motherboard. Which came out, I'm not sure how much after the PS1, a couple years maybe, but they needed PS1 games to still run on the PS2 system. And so what they did is they took this nice little chip right here, and they emulated the PS1. So imagine that this whole thing was the PS1 at one point, and for the PS2, they're basically able to shrink it down to that little thing. So this is a 32-bit MIPS processor. Look how slow it is. Wow. Here we have the new one, which is 64-bit MIPS, and it's 10 times as fast. Wow. Yeah. So that's why CMOS is important. And
what is Moore's Law?
I hope you guys learned something. Moore's Law is the idea that it's the idea that everything's getting smaller. Moore's Law.